Hello, my name is Alexander Blom and I'm from the University of Cape Town's Mechatronics lab. The focus of this work was to investigate rapid acceleration and braking motions of a biped robot to gain insight into design parameters for a physical platform. Rapid acceleration maneuvers are not well understood due to the aperiodicity and complexity of the motion. Robots and animals are fundamentally different with stiff links and rotary actuators compared to compliant legs with muscle tendon actuators. Thus, we rather use optimal control to avoid taking inspiration from nature. We selected a 5-bar parallel linkage mechanism as it has low inertia, a large workspace, is robust, and is a suitable anchor to the standard leg template. Our specific aim was to find the optimal nominal linkage length and gear ratio for rapid maneuvers. Numerical optimization was used to minimize time for sprints. This involves a model rapidly accelerating and braking across a set distance in a single optimization problem dubbed the tax day scenario. The direct collocation technique was used and the trajectory was broken up into 200 nodes, with each node allowed to vary. Thus, the total time of the sprint could be minimized in the objective function. We predicted that the model with the highest gear ratio would accelerate faster due to the availability of a higher mass-specific force. However, the optimal leg length was difficult to predict given the trade-off between stride length and frequency. We were surprised to find that all model sprint times did not vary significantly. This is the sprint of the optimal model. A parabolic curve emerged for each gear ratio variation, and the best leg length could be identified. However, these three minimas differed slightly, and you can see how close the sprints really are. It was amazing, though, to see that the motion generated had a lot of similarities to those of the biped's biological counterparts. We found that the rapid acceleration phases for all the models were similar, suggesting that the motors, with the available gearboxes, were overpowered. We identified two interlinking factors. Models could easily exert an excessive normal force and perform large leaps achieving high accelerations, but the model's feet would be out of reach of the ground, negatively affecting the forward acceleration. This video shows a non-optimal solution where large leaps are performed. The second limitation is the friction coefficient. Ultimately, we identified the required parameters for the design of a physical platform and showed that higher force output does not always result in faster acceleration for legged robots. Thank you, and come to the interactive session to learn more.